Welcome back. Now let's talk about these inferences by transformation from the perspective of validity. What we want to know is whether these inferences are actually valid. In other words, if the premise is true, is it possible for the conclusion to be false? In some cases, it's intuitively pretty obvious that you've got a valid relationship. So, for instance, with the relation of conversion, if you think about it, conversion on an E, no S is P, therefore no P is S. That is pretty much intuitively obvious that that has to be valid. But what we want to do is prove that it's valid. So how would we prove that it's valid? Well, there's a couple of ways we can approach this. We could prove that it's valid by trying to find a counterexample. Okay? So, for instance, let's say that we substitute real terms like cows and reptiles for the terms that are variables in our premise. You see, we're looking here at a logical form with variables, right? So let's make a model like this. No cow is a reptile. So that's a model. But if no cow is a reptile, then no reptile is a cow is the mechanical operation of conversion. So these are converses of each other. And the thing is that if it is true to say that no cow is a reptile, then it can't not be true to say that no reptile is a cow. So we could try to find a counterexample where this is true and this is false. But that's somewhat inefficient because, it also depends on our ingenuity and whether we're in a good frame of mind that day and all these irrelevant factors. So actually, what logicians have argued for is something more independent of our mental state or our, ability to be ingenious, right? So one of the best ways we can discern the validity is by using a Venn diagram. So let's go back to the original without terms here. I'm just going to erase some space. So let's go back to this E and let's do this. If we presuppose that the premise is true, then the relationship between the subject and the predicate diagrammed in a Venn diagram is going to look like this, right? Okay, so this is the diagram of the premise. So here's the way this algorithm for proving validity works. Diagram the information in the premise, and then stop diagramming things. If you put information from the conclusion, you'll contaminate your diagram and you won't be able to tell what's going on. So diagram the information from the premise, which is what we did here, and then ask yourself, if this diagram represented a true assertion about the relationship between S and P, would this diagram force this conclusion to be true? Force as in the conclusion couldn't be false if this diagram represented a true relationship. So look at the thought process here. If no S is P were true, then this diagram represents the relation between S and P, and the shading here in the middle means that that region is empty. And if that region is empty, then it can't possibly be false that no P is S. Why? What would make no P is S false? Well, remember from our discussion of the square of opposition, what would make no P is S false is for there to be something in the region that is shaded out. In other words, if no P is S is false, then it must be the case that there's at least one P that is an S, right? But as you see, that's impossible in the diagram because of the shading. So if the premise is true, then that means this diagram represents the relationship between S and P, and this diagram by itself, with no added information, requires the conclusion no P is S to be true. So what we will say about conversion applied to an E is it's valid. Okay, let's look at another example of this method before we tackle some of the other mechanical transformations. So let's look at conversion applied to A. So A is all S is P. That's an A. Conversion is to swap the subject and predicate terms. Oops. Okay. So notice we've applied conversion. So we start with an A, we end with an A, because the only thing we change is the position of the categories, S and P, right? So now let's apply the same method. Let's diagram the information from the premise. So here's our empty diagram. The shading goes here, just like this. All right. So now we've shaded the region of S outside of P to indicate that all S is P. Now, with no other information added to this diagram, does this diagram require that all P's are S's? And if you think for a minute, you'll realize that it doesn't require it. And the reason is because nothing in this diagram tells us whether the region of P outside of S has to be empty. All it tells us is the region of S outside of P has to be empty. So because of the information in the premise, which is the information that counts here, right? If the premise were true, then the only information we have to draw on is the information in the premise, assuming it's true. That's this. So if the diagram represents the relation between S and P, this diagram does not require it to be the case that all P's are S's, and therefore conversion applied to A is invalid. Okay? So you see the difference? In a valid situation, the truth of the premise requires the conclusion to be true. Or the way we normally put it is, if the premise were true, the conclusion cannot be false. That's valid. In a situation like this, however, if the premise were true, the conclusion might still be false. It might still be false because there could be P's that are not S's. And if there are, then it's false. So the point here is the require aspect of it, right? In a genuine, valid inference, the truth of the premise requires the conclusion to be true. And using a diagram in this way, we can prove why that is. Okay, good. So now let's take a look at the other inferences on the square of the other inferences, but looking at it from the perspective of the square of opposition, right? So first of all, we've established that E is valid on conversion, right? So if we take an E, if we take an E proposition, so that's no S is P, and we do conversion, we get no P is S. We've just proved this one. If we do the diagram, what we find is that the diagram requires it to be the case that if the premise is true, the conclusion cannot be false, right? So let's do I. So what we have is some S is P, and the conversion of that is some P is S. Now, if we diagram the premise, what do we get? So notice we're just diagramming the premise. Some S is P. If some S is P, that means there's at least one S in the P circle. But look, if there's at least one S in the P circle, then there's also at least one P in the S circle. So if this is true, this diagram represents the relation between S and P, and the information on this diagram requires this to be true. So what we can say about that is I'm going back to this, conversion is valid for E's and I's. But it's not valid for A's and O's. And we've already seen why that is. Let's go ahead and put this up. We've already seen why that is. So look, with A, but let's look at O. So we have some S is not P, and conversion will be, will tell us some P is not S. So now diagramming the premise, we get this diagram. So there's our S and P. Notice the information on this diagram comes only from assuming the premise is true. So if the premise were true, this diagram represents the relation, and this relation does not require there to be at least one P that's not S, because if it did, there would be an X in this region of P outside of S. But there's not. So that means that it is possible for this premise, the O, to be true and this conclusion to be false, which means that the O is not a valid inference applying conversion. So what we've established here is that conversion is valid for E and I, but not for A and O. Okay, so that's great. Now let's look at another. Inference here. Let's do. Put this on. Let's do the contraposition of A, and this will give you the idea. So what is the contrapositive of A? So A starts out all S is P. With contraposition, if you have practiced a little bit, you'll remember this. We keep everything the same except we swap the complements of the subject and predicate terms. So they're swapped. We keep the is, we keep universal and affirmative. So we start with an A and we end with an A. And the inference is all S is P, therefore all non-P is non-S. All right. So now let's do the diagram of the premise. Now again, we're going to put information on here only from the premise. So we need to diagram all S is P. Okay, that's good. Now, think about this diagram. This diagram has shaded the region of S outside of P. Now, think about what's being claimed in the conclusion, all non-P is non-S. What it really says is this: everything outside of P, so visualize P, which is right in front of you, and visualize everything outside of P in the universe. So everything outside of P is outside of S. And if you think about it, because of the shading of the region of S outside of P, then it has to be true that everything that's outside of P is also outside of S. And it's because of that very shading that makes it true, that everything outside of P is also outside of S. So contraposition then is valid for A. And I'm just going to tell you that it's also valid for O, but I'm going to ask you to prove that for yourself by constructing a diagram. And the other thing I'm going to tell you is obversion is valid for all four of the types. Obversion is valid for all four. Okay, so we have conversion valid for E's and I's. We have contraposition valid for A's and O's. And we have obversion valid for all four types. I'm going to do one of the proofs for you about obversion, and then I'm going to strongly recommend that you do the diagrams to prove the others for yourself. So for obversion, let's do the diagram for I. So here we have some S is P, and obversion is some keeps the same quantity, changes the quality, is not. Okay, that says is not. So now we have some S is not non-P. So remember, the whole operation is same quantity. So particular stays particular. Whatever the quality is in the premise, we take the opposite. So it's affirmative here, it needs to be negative here. S stays the same, and we take the complement of the predicate term. So P becomes non-P. So we start with some S is P, and we end with some S is not non-P. All right, excellent. Now let's do a diagram for the premise. Here we go. Some S is P. So here is SP. We'll put an X in the overlapping region to indicate that we have at least one S is a P. Now, again, we don't add any information from the conclusion onto the diagram, or else the diagram will be contaminated and it'll tell us things that aren't so, right? We put only information from the premise, and that's what we've done here. Now, ask yourself, does this diagram, assuming the premise were true, this diagram represents the relation between S and P that is asserted in the premise? Does this diagram require the conclusion to be true? Well, what does the conclusion say? It says there's at least one S that is not outside P. There's at least one S that is not outside P. And so look, there's at least one S, there's the at least one S that is not outside P. And sure enough, this X that represents at least one S is not outside P. And so this diagram does actually guarantee that the conclusion is true. So we can say if the premise were true, the conclusion cannot be false. Therefore, obversion is valid for the I proposition as its starting point. Okay, again, we've looked at the method of proof and we've looked at the mechanical transformations. Now I'm going to leave it to you to construct the diagrams to prove the rest of the operations that I didn't specifically prove in this tutorial.